And you
students are able to see.
There was a network issue. Actually, I am getting proper place.
maybe for a few minutes. I'm using
One minute. Problem is bad.
काली टोपी और एक गमछा डालना है.
So by the way, I was trying to have a panel discussion, so it was difficult.
Audible to everyone?
Yeah, audible, yes. Yes, can you hear?
Yes, sir. Actually, there was a network issue in my room, so I was shifting my room.
Okay, fine.
Some problem in the.
Yeah, if you don't want to show us your luxury house, then that's okay.
Yes, sir. So I will share, just let me share my slide.
Yeah, and I will introduce it once you are ready.
Yes, sir. Yes, I'm trying to share the slide screen. Did it share, sir?
No, we don't. It's coming.
I think it's been might be coming, right?
Yes.
Yeah, I will open the slide.
Okay, so I was telling you about panel discussion. We were trying to get it today, but somehow we couldn't get the speakers. But tomorrow, we will aim for tomorrow morning. Okay.
Just give me, sir, 1 minute.
Okay.
Yeah.
I want to see his part.
Sir, should I start now?
Yeah. So we will not be seeing your face.
I will try to.
Okay. In
do
the
it, but
I'll
there might be
introduce. In the
problem.
meantime, you whenever the internet is good, you can have your.
Sure, sir.
Okay, so it's pleasure and honor to have Dr. Jayaprakash Tripathi. As he's showing in his slide, he's a professor at Central University of Rajasthan. But personally, he's one very, very active person I have known actually. He has been, I think if I am not wrong, maybe 10 to 15, 20 projects he's running simultaneously. And many grants, he's writing books, he's publishing papers, and you can see the students wherever. So the output speaks more than what I can talk about him in words. And if you Google search, you will find his name in various works. We have been working for last many years, and our work has been published internationally in Royal Society and in American journals, for different journals. And so, and he has worked with faculties in Canada, US, Europe, okay, we can see you now. Can you hear us?
Yes, sir, yes.
Yeah. And so you can
Okay.
see he has a beard also. Okay, he's not showing his apartment.
No, sir, yes, sir. Thank you so much, sir, for such nice words. And so these slides actually I prepared in this night only because I was traveling from last 3-4 days, delivering some other talks on the Ramanujan Day.
Jayaprakash, if you can also give some brief background of yourself, what you have been doing, what work, and there are 2 culprits here sitting at the back from your group, from your research group. So you can talk a little bit about your background first, and then you can start with that.
Okay, sir. I do not have slide, but I will try to say something about that. Let me start formally thanking to this organizer of this GAM program, Global Initiative of Academic Networks, and this very fruitful workshop that you people are enjoying and getting benefit from it. And I was personally very much interested to come also, and motivated the students that they go there, we will learn and get motivated for research on the topic data-driven thinking, modeling, and statistical inference for global health challenges. So, so personally, I thank to Professor Anuj Muvai sir and Dr. Tripathi for inviting me in this workshop and giving me chance to talk something about the disease models. Uh, First of all, as sir suggested that let me tell something about my research actually that we are doing. Still, I do not have any slide, but briefly, sir has told many things. But let me tell you. Actually, I will just start the things connected that those are connected in my research with Professor Muvai sir. I started interacting with him, if I recall, in 2016 or 17. Then we have started discussing some problem in disease modeling, particularly schistosomiasis problem, and then we also have got some problem in COVID-19 human behavior modeling, particularly vaccine hesitancy problem. And also we have been publishing in some good journals like RAS Society, Open Science, Nonlinear Dynamics, and Mathematical Biosciences, Engineering, and some journal like that. But the most important thing is that I have been interacting with him and learning so many things in research, how to plan the research, how to do the research. Actually, these things are very important when you start doing the research, particularly in India, and outside the environment is something different. So, it's my pleasure to be here, and also I am very much thankful to Professor Muvai sir and Dr. Tripathi to give me chance to talk here. And also, if you are interested to work in disease modeling, so you can contact our group, and we can have some discussion with you. And after having proper discussion and planning, then we can define the problem and we can work on it. So it's not like that immediately we start working, just finding some model and giving some results, mathematical and results, those kind of things. First of all, we have to plan properly, and we have to, as I have discussed a lot with sir, that we have to have our objective actually on what problem means, what are the objective of the work that we want to do. So once objectives are clear, then only you can think about the method and about the model, which model you have to generate, or you have to model develop, or which method you have to use. Without the objective, the problem is not clear, and you cannot jump into the solution or the developing the model. So the research objectives are very much important, and along with that, then only you will explore the background, right? Background behind the problem, and what other literature review and other things are there, and then you will come to your mathematical model, and then mathematical and numerical analysis and interpretation of results, and coming to the answering the research questions, because research is nothing but answering the research questions, objectives. So this is very important, that all the things I have learned from him during this last 10 years. So you can also Google if you are interested to see my work, and my work connected with the Professor Muvai and Dr. Tripathi, and then if you are interested, then we can discuss about that. So I think with this brief background, oral background, I am not having any slide, otherwise I can show you many things there. So we have also a lot of collaborative work.
भाइयों क्या कर रहे हो यार? मुझे फोन करते हैं तब ये
Hello.
Yeah. So yeah, I guess we got disconnected for 1 second.
Yes, sir. Automatically I was disconnected. I am guessing actually the problem.
Yeah, it's fine. You can switch off your.
No issue. I think, sir. Now it is saved. Okay.
Yes, it is.
Yes. So by saying these words, we are all are connected throughout the world, because there is networking, mobiles, and online. You can chat, you can message, you can email. Then we can discuss about the research work. if you feel comfortable about that. So, as I told you that I have prepared these slides, there might be some typo mistakes also, but I will try to rectify those as I will go ahead, because throughout the night I prepared and in the morning also. So I will basically talk about the, you see, when you talk about the disease models, so what is the most important thing? Disease models when you talk about, then at the same time mathematical, particularly mathematical model, then actually it is dynamic in nature. Derivative of the different compartments that I think you might have learned about all small things, definitions, compartments, and different kind of rate of change of those compartments. So you get the derivative of those compartments because the population from one compartment moves to the other compartment, so rate of change is there. And if rate of change is there, so derivative you have in the left hand side. But what is the most important thing that actually changes the scenario in the dynamical analysis of the model, or you say prediction of the infectious people, or whatever you say about the model, what is the most important thing that is actually important is the interaction between the compartments. How the different compartments interact. In the you can understand a similar fashion as we do in the species model, right? In the ecology. So similarly, one and two compartments, suppose one is susceptible, other is infected, other is recovered. Then how these interactions are there, that decides what kind of dynamics and what kind of fitting and predictions and simulation results you will get. So that should be understood properly before we are going to model a particular kind of disease, and also it changes as the disease changes. For the different kind of diseases, you have the different kind of interaction between the compartments, and hence to the interaction function that you model changes accordingly. So we are going to focus on that. So I have written the title like non-linearity in disease models. So this non-linearity comes by easy to complex, right? When we start with the linear with the linear interaction term, and then we go ahead slowly and we enter into the linearity and then the highly non-linear interaction terms between the compartments. I think I am able. You are listening me properly? Yes, sir. Please, just can you answer me once?
Yeah, we can hear you.
Yes, sir.
We can hear you.
So I have tried to divide my talk. There might not be some proper sequence. So let us come to the slide. Firstly, actually, I will just brief you in the first slide that how this non-linear means. There are different kind of mathematical models, right? When you talk the mathematical models, these mathematical models are just a part of the mathematical model. Mathematical model is like in that we have a different type of branches like disease modeling, disease mathematical model. Then we will come to the epidemic model and we will talk about particularly incidence, that the non-linearity will come in this incidence. Then the linear to saturation, the simple non-linearity, the first simpler non-linearity. Then we will come to the other non-linear incidence rates, and then I will talk some crucial questions. Actually, those I have been thinking to just discuss with you in disease modeling. Some simple questions are there, so those are very important when you discuss somewhere that why we are getting such kind of scenario like constant recruitment, constant population, standard incidence, all those things. So models are basically two types. There are different types according to the nature of the models, but here we are talking about the linearity and non-linearity. So accordingly we have the two kinds of model. I have just taken the example from our disease model, but there are different kind of examples we can take for the linear non-linear model. So you see the first model, di over dt equal to beta I. So it depends on I is our dependent variable. So it depends on I linearly. So it is called linear model. So how you define the linearity? Linearity is defined by the right hand side function. The interaction between the dependent variable that you take mathematically. Don't think about the infectious population, but the I is the dependent variable. If we are not having the non-linearity in I, or if you are having more than one variable, dependent variables, and you are not having the non-linearity in the dependent variable, then the model will be called linear. So what do you mean by the non-linearity in dependent variable? Means simply there is not product of these dependent variables, higher power of dependent variables, and those functions will not come like transcendental. They should not be the argument of the transcendental functions. Okay, but those functions we are not going to include like time, cost, and exponential. So non-linearity comes in this way in the simplified form. But then when you try to define the linearity and non-linearity with the help of the more rigorous mathematical term, then we have to go for the linear operator, and you have to apply the linear operator here. If the function follows the linearity, then it is linear, otherwise it is non-linear. So it's a matter actually of discussion. We can discuss about this in some slides, but here we are not going to into that deep. So linearity means simple. The function in the right hand side should be linear in the dependent variable. That's it. Okay. Those dependent variables are what in your disease model? These compartments: susceptible, infected, and recovered. They are your dependent variables, right? In those variables, when they interact, then there should be linear terms in the right hand side. Like you see this point, di over dt equal to beta I in within bracket 1 minus I. So what we are taking here, rho depends on the interaction between variables, right? So it becomes non-linear if the I square is there. So this is the non-linear logistic growth rate, and this is the linear growth rate. Okay, and similarly, as I told you that depending on the nature of the classification, we have the different kind of mathematical model, static dynamic model, and then again depending on the time that you are taking or the scenario that you are modeling. If the discrete time is important there, time is in the discrete steps like days, weeks, hours, then we will get the discrete model. Here one example is there, and if the time is continuous, then you can get a model like SIR model, SIR model, SIS model, and other models like that. So let us don't go into that deep actually, otherwise we will move to the mathematical modeling part. So why actually epidemic model? I hope that you have been discussed, but I will just tell very briefly. Epidemic model is mathematical or computational framework, right? So when you are talking about epidemic model, then it is not required that you always develop the mathematical equations. That's why it is a computational work also. You have data, then you can compute, you can estimate the parameters, and you can predict the scenarios, you can go for the simulation of the thing. So why we do this? To describe spread of an infectious disease, because we are trying to learn what kind of dynamics is there, or what is the future protection there, right? How many infectious persons will be in coming days. So and you want to explain the scenario also, and you want to tell something about the control strategy that you are going to apply, like intervention schemes, different kind of intervention schemes. So for those reasons actually we are going to have the epidemic model. And like very simple question I have written: how fast will a disease spread? When will the infection peak will come? So and how effective the intervention will be, like control strategy, vaccination, isolation, treatment, other things. So if you want to particularly answer these questions, or you can ask that will the disease will die out or persist for longer time? Somebody may be interested in the disease dynamics also. What kind of dynamics we are going to get? You want to predict the outbreak size and duration. So there are different kinds of, and if the disease is very kind of fatal, then these questions becomes more important. Like you have seen the COVID-19 in the recent days. So these are the questions, actually basic questions. Those are the questions of our research when we do, and ask the question becomes more precise when we do the research in a particular kind of disease. Then actually these becomes our research questions also. So here coming to the nonlinearity part, I have just table, but this table will come back again when we will go ahead. So here I have written the we are going to define the incidence rate. So these are the mathematical form of the incidence rate. You might be seeing in some models that we have been discussed. Here I have written here the 5 kind of incidence rates. One by one we will come to this. But all the incidence rate, whatever you are taking here, they have some particular reason why you are taking such kind of incidence rate. But in the different kind of scenario, the different kind of incidence rate might be pretty well. Okay, so we'll come back to that. So I think, sir, SIR model has been discussed properly. Should I take that?
Yes, 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 it has been.
Okay. So let me just take the important points. So rate of change of, yes, you see there are three compartments SIR, and we have taken the population and total population is constant. So DS over DT, you see we have taken, what is the incidence here? The number of individuals who become infected per unit time in epidemiology is called incidence. So when the number of individuals those become infected per unit time, then they will come out from the S class, control class. So we are taking DS over DT is nothing but, and we are not including other kind of interactions or any kind of thing. So simply we are just taking the incidence term minus incidence, because they will get out from the susceptible class. So if I can get this incidence term, then immediately this first equation will be modeled. Okay. So the you see we take the CN is the number of contacts per unit of time this infection individual makes. So here we assume that the number of contacts made by one infectious individual is proportional to the population size with per capita contact rate C. So it is CN, right? So S by N is the probability factor, that is the probability that the contact is with susceptible individual. So if S by N is the probability that one susceptible individual has the contact, so if I multiply with the CN, the number of contacts per unit of time the infectious individual makes, then we will have the number of contacts with the susceptible individual that one infectious individual makes per unit time. And if we take that successful contact, right, that convert into the transmission, the probability is P, then immediately this PCS is the number of susceptible individuals who become infected per unit of time per infectious individual. And if we take this PC equal to beta, that we call the transmission rate, and the beta SI is the number of individuals who become infected per unit time. And from this beta SI, if I take this, just you take the per susceptible individual, what is the infection rate? That is beta I, that we call the force of infection term. And this beta I actually, this lambda T actually changes that per susceptible individual infection rate, or you can say what is the infection risk, right, by a particular infectious individual, that is called the in unit time, that is called your course of infection. This lambda T actually is responsible for the different kind of nonlinearity. As we will see this, when we change this lambda T, then we have the different kind of nonlinear incidence rates, because when we multiply this lambda T by S, then immediately we have the incidence rate. So lambda T is called the force of infection, and beta, and the coefficient beta is the constant of proportionality, that is the transmission rate coefficient. So so the first term is model, right? Once you have the incidence, the DS over dt equal to minus beta SI, and similarly we will go to the second term, because from the infectious compartment the people are also getting out. So if we take that those individuals who recover or die leave the infected class at constant per capita probability per unit of time, that is alpha. So alpha I will be what? If I multiply this alpha with the total infectious individual, then it will give the number of infected individuals per unit of time to recover. So they will go to the other class, right? Recovered class R. So we will have the di over dt equal to beta Si minus alpha I, and then C alpha I will go into the immediately to the recovered class. That are particular kind of assumptions, right, that we are taking. So we are getting this kind of model. So these are the three equations. I hope that you have been discussed this. So what is the linear here that we have to see? There are also two important things when you are going to model. So let me ask you a question, somebody of you can answer. Why the initial condition in an epidemic model? Anybody of you? Why we take the initial condition? Very simple question. You can connect with your differential equation with this, right?
Why do we have an initial condition in the differential?
Yeah, anybody can answer this, then we can go ahead without asking about this.
We're doing the time dependent analysis. At the beginning, what is the actual number?
So the response is that we are doing time dependent analysis.
Sir, to like
Okay.
we are framing system of differential equations. So
Yes.
so initial value problem, this is the kind of initial value problem we supposed to transform that study in IVT form.
Yes. So this is initial problem is correct, but you are taking the initial condition, right? Initial condition, and with this initial condition, we want to start, right? Some populations will be there at the initial level, and then you want to predict you want to know the future outcome. Okay, and with this also, you also become interested that when the solution starts with this condition, then it should follow a path, a single path. Otherwise, you will be in trouble, right? If you are taking the different kind of path. So actually, with this initial condition and the differential equation, we become interested. Mathematically, we want to see the uniqueness of solution, right? So that we have the unique kind of prediction. Otherwise, if you have the 10 prediction, then you will be in trouble. Okay. So we can combine this initial condition, differential equation, and then the uniqueness of the solution. And when we formulate a model, why we need to be concerned with the unit of the quantities involved, right? Here you see, we do the dimensional analysis, right? The system should be dimensionally homogeneous. Otherwise, the system will be incorrect. This is the one way how we can at least know that in the left, what is in the left, that is in the right. Both the unit of both the quantities in the left and right are same. So your system is dimensionally homogeneous or dimensionally correct. We have to see that, and in this model that we have developed here, actually this is happening. If you will see, okay. So in the left hand side, what is the from the first equation what we see? What is the this left hand side? SODT or AODT or DRODT. So per unit time, number per unit time is what? This is the unit of the left hand side, and when you go see the unit of every term in the right hand side. See, right hand side, for every term, why I say? Because the second equation there are two terms. So the units should be number per unit time. Okay, so that will come. You can analyze this, right? So beta must be 1 upon number of people, unit of time. So unit of the first term is the per unit time, and similarly the other term also has a per unit time. So number has no unit, right? Number means some number, so you can relate that. So the left hand side and the right hand side both have the unit per unit time, 1 upon unit of time. So it's okay. Okay. Similarly, what is the message from here? You can at least, whenever you are trying to model some new problem, then you should have these ideas that whether my equation is dimensionally correct or not. It's not like this. In the left hand side you are having the horse, in the right hand side you are having the elephant. Then the equation will be incorrect. At least our equation should be correct. Then only we have to talk about the computation and estimation and the mathematical analysis. So these are the some things that we have to be careful about that. So now coming to the linear to non-linear. So this is actually FSI is linear incidence. Why we call it linear incidence? Because whenever you take a force of inflection, then this is what? Beta I, right? So it is linearly changing with I. When I change I, then beta I change is the sum multiple, constant multiple beta with I. So it's a linear graph, right? Beta I, force of inflection. So it is called linear incidence. So but there is some problem, right? So whenever some new incidence term will come, that means some other incidence terms, those are already available, they have some issues. So what is the issue here? If I take the I tends to infinity, then incidence tends to infinity, this is unrealistic. Inflection starts, this is okay. But when you say that it will go on and go on, when I increase it, then this is increased. But this does not happen. As you know, that there are different kinds of interventions, limitations are there to actually restrict this infinite growth, right? So we have to just be very careful, and mathematically actually it is shown here. You see, if I take initially the population S is S naught, because for the initial time, for the starting time duration, then you will replace this S by S naught, and immediately you will get IT as the exponential growth if beta S naught is greater than alpha. Then it will actually go and explode. But actually this does not happen with the real academic data also. That do not follow the pure exponential for a long time, because people change behavior, intervention happens, and contracts saturate. Okay. So that means we need some other kind of incidence rate, because it will not work for the longer duration. For the shorter duration disease it is okay. Okay. So linear incidence often, this is overestimating the new cases as we have seen, right? What is the overestimation here? See, this is overestimating the cases. For the shorter duration is okay, but for the longer duration is going to increase. So overestimating. Unless intervention effects are absorbed into parameters. So non-linear form, what should be the non-linear form of this? How the non-linearity will come? What was the your force of infection term? Force of infection term was the beta I. So we have to modify this beta I here. Okay. So beta I, how you will modify? So the idea comes in mind that when the I increases after a certain time, then this lambda t should decrease. Okay. So in that with that idea actually, this beta I is divided by another term 1 upon 1 plus alpha I, and this alpha is actually the saturation term, right? That saturate the incidence rate, this forcing term. So lambda t, that was beta I, it is multiplied by 1 upon 1 plus alpha I, and now your forcing term is beta I 1 plus alpha I. So when you multiply this by the most susceptible individual, then FSI equal to beta SI upon 1 plus alpha I becomes your incidence rate. And in that sense, because lambda t is beta I upon 1 plus alpha I, this is non-linear, then we say that our incidence rate in that model becomes non-linear. Okay. Go ahead. So this was the non-linear incidence rate. We will come back to all these things again. So another one is the standard incidence rate. So can somebody answer why we actually take the standard incidence rate in place of this linear incidence rate? One we have discussed, right? Non-linear situation kind of incidence rate. Standard incidence rate.
Anyone has an idea?
Yes, there are so different kind of regions, right? 3-4 regions, but one region at least somebody of you can tell.
Anyone has an idea? I think I heard many people doing epidemic models.
Yes, sir.
No, I'm
This is not like dividing by total cost.
state level. It's
Yes.
well,
As you see,
yeah, I don't think they have any answers are here from the audience. So go ahead.
Yes, we will come to the answer. Actually, let first we model it. So you see, it's not like that every time that everybody will infect to everybody, right? The infectious person. So there are diseases; those are particularly prevalent in the childs, but they are not prevalent in the older people. So, and also there are some kind of restrictions also that a particular individual can infect the fixed number of contacts per time.
Yes, sir.
So if the scenario is like that, then in that case, and also there are some other reasons also, in that case you have to follow the modeling of the incidence rate, standard incidence rate in your model, beta SI by N, and how it comes. This is the standard for human diseases, because this actually happens if you talk about the wildlife diseases or for the wild animals, right? In the jungle of the wild. So in that case actually this will not be followed, but in the case of the human diseases, this case is very important that individuals are are restricted, are somehow they have to interact the fixed number of contact. Okay, so probability that a contact is with the infected person is I by n. So when we actually multiply with the total susceptible, if beta is the effective contact per unit times beta s, then immediately what you have beta s into I by n, and the final incidence rate is beta s I by n. Then your SIR model will be what? This the term beta si will be replaced by beta si by n. Okay, beta si by n. And the model is with the standard incidence rate. So in a particularly you can say that the standard incidence rate models disease transmission by assuming E is a fixed number of contact per unit time. It's not like that everybody is having the same number of contact, right? There are three. So we take the I by n, right? That multiplies with the all the susceptible individuals. So leading to an incidence proportional to a fraction of infected individual, that is I by n. Okay. So there is a other kind of scenario by which we can have the non-linearity into the incidence curve. So actually, when you see the modeling of these non-linear incidence rate, then actually by the different ways or different names, you can tell. So one term I have just got here, I have taken here, this is a fear, right? Psychological effect. So it is also a part of human behavior. Human behavior are different kind of behavior that human shows when the disease outbreak takes place. One behavior is a fear effect, other is the vaccine hesitancy. Some people they are keen to take the vaccine, but some restrict themselves to take the vaccine. So vaccine hesitancy is another human behavior. So we are just talking about fear effect. So here, as you see, that it will decrease this incidence rate, right? Because once you have fear, then you are not going to interact with the people who, if you know that this person has the disease, you will avoid the risk of having the infection. So one general idea comes in mind that it will actually reduce this incidence rate, right? So the fear, as the fear disease, people avoid contacts, isolate vulnerability, wear mask, reduce mobility. So what is the result after that? Effective transmission rate decreases as infection increases. Okay, so that means we have to model a function into the transmission rate so that the transmission rate decreases as I increases, the infection increases. That is the idea, general idea. So we have to get such kind of function. So why fear must be included in the incidence rate? Because again, this is the problem, right? As we have modeled situation kind of incidence rate. Similarly, this is your classical incidence rate, beta si. So in this, again it will go to infinity as I tends to infinity, predicts unchecked exponential growth, predicts, okay, growth slows even before immunity dominates, growth slows even, it is repeated as I told you that I made this slide not rectified, so now it is rectified, okay. Okay, so as I told you that transmission rate will decrease, so FSI, that by beta si, it should be multiplied by a function gi that has certain kind of property so that this total FSI is decreased. How we will do this? So you have to think about the property of gi. So once you say that beta si should decrease, then the gi should take value between greater than 0, less than or equal to 1. Otherwise, how you will tell that this will decrease? So whenever it will be 1, then this is your the linear incidence, classical incidence rate. So this is the one condition. Other is its rate of change should decrease, right? dgi or dt should be less than 0 because it should decrease. Okay, then only it will decrease the beta si. So saturation kind of incidence rate was beta si upon 1 plus alpha I. This is again, there we have talked in some different way, but when the fear is moderate behavior can be compensated up to some level, then the effect of the fear can be modeled like this, and beta si will be this term numerator, and gi, that is the fear term, will be 1 upon 1 plus alpha I will be multiplied by this. And I want to connect this one. If you are interested to work in disease ecology or the ecology, then you also see the fear there, right, between the species. So the species that is eaten or consumed by other species, then that gets here, and due to that, as you are getting here the fear term in the incidence rate, in that way you get the reproduction get reduced because they are in fear, so they are not going for foraging outside properly. They are making them bound in a certain area, so that their growth rate get decreased. And in the first term, like growth rates, we have the function like this. So the idea is also connected from there. So here it is also connected here. But once the fear is high and situation are panic, then we take the also quadratic term, because here it just shows that if I increases, then this 1 upon 1 plus alpha I square decreases more fastly, because here you have the I square. So fear grows faster than infection. Yes, it will grow faster than infection because I is the infection and I square is the denominator. And similarly, if the situation is more panic driven response is there and very rapid behavior suppression is there, then in that case you can model the fear with the exponential term. Okay, alpha I everything is not positive, so e raised to power minus alpha I will be this will be decreasing this beta si, right? Beta si. So there is a exponential fear function also. So actually what I want to tell you that, you see in what way actually we are making the linear incidence into the non-linear incidence. There are different ways by which you can model your function according to the disease, the scenario of the disease. So force of infection with the fear effect, we also generalize it. Lambda equal to FSI upon S, this is your force of infection, right? That you tell that risk per susceptible decreases as fear increases. That we have taken alpha I power P. So this power P, P can be between 0 and 1 if the fear is like moderate or like that, and if the fear is much higher, then you can take P is greater than 1. So accordingly you have the different kind of non-linear terms model, the incidence function model by the non-linear terms. So actually we have to generalize this idea, and then accordingly we can understand the every kind of non-linearity. And here I have written some more non-linearity. One is this FSI, beta Si upon 1 plus alpha S plus gamma I, and this is more appropriate. This is called the mutual interference term, gamma I, and here this is widely used in ecoepidemics, right? And this is very much popular in the ecology, that is called Bennington functional response there. So that kind of scenario also we take, and we also generalize it by taking the its generalization, that is called problematic incidence rate. I am not taking it here, but in this way actually we have the generalization of this non-linearity into the model and giving the proper reasoning of that. As here you see, I just taken a graph from this disease, this ecology. People are sitting there, they work in ecology, my students. So, but when you take the I, right, I an infectious individual and I increases, then you, whatever the function you have taken, right, you see these functions, saturation kind of incidence rate, okay. This beta I upon 1 plus alpha I, okay. So when you try to plot this, then you have the saturation kind of incidence rate. You will have a plot like this, okay. So as the function changes, Bennington changes functional response, problematic functional response, incidence rate, or the heavy, the much fear is there, and the moderate fear is there, and the linear incidence is there, and this graph is there. So similar kind of actually what happens, this is not going to model when the infection is become higher and higher because the things become aggravated. Suppose infection is increasing and there are more infectious individuals, then the susceptible population will be very small. Then what is the idea behind that the infection should increase? it should saturate, right? At that time, then we have to model it by we have to capture this kind of scenario by the saturation kind of function. And here just I have taken a graph of the linear versus non-linear fitting. So you see this blue line, this is the COVID-19 data, the real data is there in between, and then the linear incidence fit is given by this red line, the red graph, and then this non-linear incidence is given by this graph, right? So when you will see that which one is for the longer time, which one is going to be the more better, having the more better fit. So it will also depend on the disease, right? Which kind of disease you are going to take. If the disease is for a smaller duration, then the linear incidence may be better. But for the longer duration, you are seeing that it is much closer to this other nut, right? Real nut. So, sir, how much time we have now?
How much time do you need?
Sir, 5 to 7 minutes, 10 minutes.
You have 15 minutes.
15 minutes, okay. Okay, so I thought that you people, some of you might be new and some of might be aware about all these things that now I am going to talk about. So I just written some questions, right, that comes in our mind many times when we see the mathematical models of different kind of diseases, this compartmental model. So I have written here some questions. Let us just diagnose that why actually they are there. When can we assume constant total population in epidemic model? Anybody up? Yes.
When there is no immigration or any
Very good. There are so many reasons, right? It's one reason. Yes. So we are going to discuss in broader in different ways, right? What are the ways how we can justify this assumption when we take in the modeling. Short time epidemics are there. Epidemic duration is short compared to human lifespan. Then actually we take the total population is constant. Epidemic duration is short compared to human lifespan, right? Short time epidemics. And as you told that natural births and deaths are negligible, immigration are negligible there. And for what disease actually it might be the useful sometime. For influenza, that is for shorter duration, right? Seasonal. And for COVID-19, short waves, not for the larger waves. Okay, measles outbreaks. So no demography included like SI, SIS, SIR, SCIR without mortality. Indicate disease does not cause death. Disease is what you want to say? Infection is non-fatal, not much fatal. Like common cold, some seasonal infection, as we can hear influenza. Population is closed, as you told very correctly. No immigration or immigration is there. Population is isolated. If it is isolated, then no immigration will be there. So school, hostel, prison, hospital, ward, like this. Mathematical also you see, it's not like that we are going to always compare with the real scenario. Sometimes we also we take this in consideration that total population of the model is constant for a mathematical simplification or mathematical factibility. By doing this, analytical study becomes easier. Stability, basic reproduction calculation, and bifurcation analysis, everything become much easier, right? Much simplified. So, but this is a mathematical angle. But if you want to the precise answer, then you have to see the what kind of disease you are modeling. That we have to take care. So, am I audible properly?
Yeah. Yeah,
Okay.
you are.
So, and then if you say that when we can take the total population is constant, then again the question comes in mind immediately that when we cannot take total population constant. So, just reverse everything, right? Whatever we have learned there. So disease induced death rate is there. Like if you have the COVID-19 severe waves, plague, Ebola, then we have to consider this. Long-term epidemics, endemic diseases are there. Because in the case of the long-term epidemics, then what you say that the infection duration is negligible in the period of the lifespan, it will not be considered there. So time scale is year or decades, births and natural death matter there in that case, like tuberculosis, HIV/AIDS, malaria. Demographic effects are included there, and in that case we have to not take the total population constant. Migration and mobility exist in that case. Like sometimes what happens that refugee movement is there, right? You cannot avoid that. Immigration and emigration is there. Urban-rural mixing is there. So in that case, you have to not take the population is constant, right? Vector one or multi-population models are there. Age structure models are there. You are considering the age structure, then you have to make a different kind of groups, age groups, and we have to not take the total population is constant in that case. So the summary is that the total population can be assumed constant in an epidemic model only when demographic effects and disease-induced mortality are negligible over the epidemic time scale. This is very important, epidemic time scale. Okay. Now next question is, why do we take the constant recruitment rate in some epidemic models? So again, if somebody of you can tell something, then we can go ahead.
Anyone has a response?
These are the very simple questions, right? But you should be prepared, right? When you are going for interview and for job and different places, then you have to answer these things.
So sir, like in isolated place, it is a demography and a specific population. So there are natural processes of the birth and death. So it remains, if there is no epidemic or intervention, then it remains at a constant value. So that's why we try to model initially like that.
Correct. So again, there are different ways we can explain, right? I am not able to hear properly, but you might be very correct. So recruitment rate is what? Rate at which new susceptible individual enters into the population, right? Through birth or immigration. Anyway, they can enter into the population. This is recruitment rate, correct? So a constant recruitment rate means new individuals enter the population at a fixed rate. The rate is fixed for all the time, independent of current population size. It is not depending on the population size, right? So again, there are different reasons behind that why we take this. Mathematical simplicity or flexibility is one reason. What is the mathematical simplicity here? Mathematical simplicity is that you are easily able to prove the biological feasibility of the model, right? That boundedness and stability and everything. Stability is properly done. Endemicity, I think, will be obtained in the model, right? When you take this constant recruitment rate. So in that case, these things are there. In the case of the mathematical simplicity, long-term disease modeling like tuberculosis, malaria, HIV, population size stabilization, as I already told you. Immigration dominated populations, refugee camp and urban areas, birth are approximately constant per year in large population. Okay, for the large population, births are approximately constant per year. Mathematical advantage is the ethnic modeling that I already told you. So they are in the different angle we can see this. Why we will take the recruitment rate constant in an epidemic model. So constant recruitment rate is used in epidemic models to represent a speedy inflow of susceptible individuals, particularly for long-term epidemic diseases. Long-term epidemic diseases while maintaining mathematical flexibility and bounded population size. आपने देखा होगा कि जब आप ये नहीं लेते हैं constant recruitment rate, then you actually struggle while you are going to prove the population bounded population size. In that case, mathematically, right? We have struggled in one or two this articles. Okay. So when constant recruitment is not appropriate, in that case, when the population size was large, then it was appropriate. But when the short-term outbreak or small population, then actually we have to be careful about that. Why and when mass action, density dependence, incidence rate, that already I have discussed, right? I think things was clear when we were trying to model SIR model, okay? So contact rate increases with population density. Beta SI means when I increases beta SI increases. So more people, more contact per person. Typical in animal population are confined environments. Wildlife epidemics, bacteria in culture, insect populations. This kind of scenario is more prevalent, right? That gives you the exponential kind of portion curve. Okay. If small or fixed spatial area will be there, then you can model like this. No social structure or behavior change is there. Then you can go with this linear incidence rate. Okay, no limitation on contact, random mixing is there. But again, the same question comes that we have already discussed. In what scenario we should take the standard incidence? So each individual has a fixed number of contacts. In that case, large human population is there, like social network, limit interactions is there, because many times we have to have the social structure, right? Social structure is there. In that case, the interaction becomes limited. In that case, we have to take the beta S into I by N. So this is going to interact with the fraction of this intrinsic individuals. Variable population size is there, scaling by N, keep transmission realistic. Long-term academic modeling is there, avoid unrealistically large infection terms. So again, just I want to tell you one work actually we had done with Professor in the collaboration of the Professor Mobay sir. So many times what is happening that in the disease there is a heterogeneity, right? Heterogeneity can come in a different way. There might be the geographical heterogeneity, there might be the heterogeneity due to your behavior, individual behavior. So it can come in different ways, right? So like if you see the heterogeneity that comes by the human behavior, then what kind of heterogeneity comes due to the vaccine hesitancy that we have considered in this work. So due to this vaccine hesitancy, we have to group the population. We have to divide the population into different groups. So what we have done in that case, we have divided the population into two groups, right? One is H or resident population, other is NH or non-resident population. So the model that you get becomes the multi-group or two-group model. Okay. In that sense, actually, we have modeled this by considering the heterogeneity into the behavior, and we have actually done a very unique kind of modeling in this case. Actually, this model and this work becomes unique because no such kind of model people have presented in the case of the human behavior, hesitancy, and heterogeneity. So this work actually we have done. This I am showing you the model. So there are, if you are interested, then we can discuss in detail, right? Every assumption is very clear. We have just given everything very properly, and how the transmission between the SH and SNH is there, SNH and INH is there, SNH, DNH is there, INH to RNH is there. So everything has been modeled with proper logic and reasoning. Okay.
Maybe we can, Jayaprakash, I think we
Yes.
can share the link of this paper with them and they can go over it. I think with the
Sure, sir.
on screen.
Yes, sir. I will share today. So about the references, they are not proper because they are the other references. But if you are interested, then I can provide you. You have to also know some good books. If you are going to start the research and you want to understand the modeling part and these kind of things that we are discussing here, then you have to read some good books in which these things have been introduced. Not like you are taking one paper and they have written some perspective, some objective. In that actually they might not be explaining all these things clearly. So you follow certain books, some good books, and then you, when you have some background, then you come to the model formulation and the parameter estimation. Okay, thank you so much. I think I have.
Well, thank you, Dr. Jayaprakash. So, what was the gist of this talk actually? You can give me one line answer. What was it trying to stress upon? So we presented. Let me backtrack the question. when we presented SIR model, what was the interesting part there? There was non-linearity.
So should I?
Yeah, you were saying something?
Yes, sir. Should I answer me? Should I answer? Or you
I'm
want
asking
to-
audience.
Okay, sir. Yes, sir. Yes, sir.
So,
This is non-linear incidence.
non-linear, so beta SI, that's the only quadratic term.
Yeah.
Rest of the term were linear. If that term would not be there, it would be, we know the solution, exponential growth or exponential decline. We know. So the things becomes interesting by that non-linearity. And the other non-linearity that you put due to underreporting, due to various type of mechanisms. So his talk today was talking about mechanisms, the non-linearity choices. And he was linking it to the real life. That's the interesting part. And he was giving an example about fear, right? And it happens all the time in the disease setting. COVID, we were scared about like getting infection. And people did all sort of behaviors. So how do you capture these things? We are very weak in behavior models. This is one way to capture behavior aspects. So his work, he worked a lot like that. He's showing very simple these non-linearity terms which is causing, and remember that outbreak, there are different types of disease count cases. It could be very simple, and then this is very peak, and then small, and then very high. You see some COVID data, for example, that is what it looks like. Simple transmission dynamics will not be able to capture that. And therefore you need this type of non-linearity. But you have to understand what is causing that data to occur. It's a mechanism building. You are putting the drivers in the model to imitate the data that is observed in the field. Does that make sense?
Yes.
So his talk was very interesting. It's the heart of the problem. If we don't know how to capture what has happened in the past, history, then how will I predict it future? If I do a bad job in capturing how the curve look like, I will not get a good curve in the future, for sure. So this is something is what he was talking about, and he's calling it as a mechanism. And there are different mechanisms that you build in such models to capture it. So this is very interesting work, and he has done many high-level nonlinearity. He is showing some examples from it from a different research. Okay, so any questions on this to Dr. Tripathi?
So, two questions.
Louder so that he can see. There is a question, Dr. Tripathi, for you.
The first question, share these references which you mentioned, the books to study for the models. And second question is, like in last work you showed the means this talk was on the non-linearity by the mathematical expressions. We are capturing the non-linearity by the mathematics. So when
Good
we
point.
develop a complex network model for the epidemic, then how we there, like maybe many views can be there. I have not seen one, but how in network models we capture the non-linearity or such kind of heterogeneity. When we develop a network-based epidemiological model instead of mathematical model.
Can you hear the question, Dr. Jayaprakash?
Yes, yes, sir. First question is related to books, right? You are talking about the books.
We can,
Yeah, you can be shared.
Yes, so
you can share with us, you can share with me, and I will share with you.
yes, so you can see the book of this Maya Marcheva. This is a very simple book that firstly you can study if you are not studied the disease modeling, and then you can also follow some other book, Anderson and May, and this
Are you
anti-decaying book.
Are you sharing any?
There are so 3-4 books are very good books that you can see. So and also those books have been written with specific purpose, right? Some books you have the good modeling part, in some books you have the analysis part, and there are books those are very simple that you have to study the first, like Maya Marcheva. So, second question, you are talking about the network problem, right? So I do not have much idea because I did not work in network modeling.
I think
So-
Shichen will be talking about it tomorrow, and he can mention this. Remember this question and address it. Go ahead. Actually, you were saying something. Go ahead. Complete it.
No, sir, you can add on to that. Actually, I have worked on a problem. It is having the dual approach, right? One is the differential equation and other is the network approach. But actually, we have not discussed that how actually we can have the what kind of are you formulating some kind of function is there? How you simulate that?
Yeah, sir.
Can you give
How
some
we
idea?
will capture, like in mathematics, we have multiplying or dividing means non-linear saturated incidence. We are trying to capture the fear effect and this from the model or modeling. In complex network or network theory, it is also used for the modeling.
Yeah.
So there, how do we capture these effects of the real situation?
If you allow me, I can add few things.
Yes, sir. Yes, sir.
Yeah. So first of all, I think what we are getting trained here is not about tool. It's about thinking process. So asking about, how is this method have these things? Method is always chosen from based on a research question. Okay. So that's one thing, to ask things in terms of a thinking process rather than, I know this method and how does this thing work. That is first point. Second point, in network model, to answer your question, in network model, what is network model?
The
That
interaction.
you are given with the edges
Yeah.
of a node, which is a contact.
Yeah.
Which is a contact. So it's the weight of the edges is what influence the infection process, right? So you can put weight different time. You were saying something, Dr. Tripathi? No, I think he's talking. So the weight of this thing decides whether a person is fear or not fear.
Yeah.
The contact will result in the infection to what intensity that contact will result in infection. Does that make sense? So basically it is modeled. So network is something different. Network is just how people are moving and how edges and links are changing over a period of time. That has nothing to do with the infection process.
True.
But as soon as you start building
The infection
the
process.
width of the edges, skinnier width or fatter width based on the parameter on top of it, you start to describe the influence of other person on the other person. Does that make sense? What I'm saying? So it's the weight of the edges define the infection process. Now, how do you aggregate that? That could be weighted average of some sort.
Yes.
To know the exact influence process. There are different, also in the network model, there are different ways to capture susceptible, infected. It's not always captured the same way as in homogeneous population. There are separate models for that. And maybe which model, you will show some things on that tomorrow. Okay. So he will talk about it and we can talk about it. But remember this is about you are building the fear. How do you build a fear? The contact will become stronger or weaker based on the fear. If two people are more fear, they will stay back at home. That means the contact is weaker. That is what it is changing. Right? Does that make sense or not? Now you can build this thing in a very non-linear way based on your reasoning, based on your assumptions, but it is just the strength of this connection which will increase or decrease. Maybe it will increase and decrease in a linear way, or it will increase and decrease in a non-linear way. So it's a functional form, but it is an edge weight which will change. And then if I am talking about this node and there are 10 edges connected to this node in a network, then this node is an individual, susceptible individual, then it will be a weighted average of these nodes. That is an intensity of an infection this person will get. Does that make sense?
Yes.
So It's the same idea. It is not very different, except you are now adding for each edges separately rather than aggregating it one thing in a homogeneous model. In homogeneous model, you don't have the separate edges. Every person is assumed to have a same number of contacts. Any more questions? There was few more questions quickly.
One simple question.
If you can be loud, you can.
Yeah, Dr. Tripathi, Vicious on this side. You mentioned about fear function GI, right? So a few fear function you mentioned in your presentation. So I was interested in knowing how are you selecting those kind of functions in a particular form only.
The functional form. What he's saying is
Right, here is in one case 1/1 plus
really
alpha
good
e,
question. Really good.
and
Yes, yes.
1/1 plus alpha. How these functions are being selected.
Okay. Okay, you see, first of all, if you want to get that what function we have to model for a particular kind of behavior, like this is the fear, human behavior. So you should think firstly, the first idea should come in your mind that what kind of effect it is going to lead, firstly. Whether it is going to decrease that transmission term or it is going to add into that, right? It is going to increase that. So once you have this idea, and then you have to think about that kind of function, and at the same time you have to also think about what are the properties those should be followed by that function, so that if I construct that function, I write that function, and we put with the transmission term, because either that behavior is going to lower down the transmission or it is going to add into that. So accordingly, you have to choose that function and the property should be followed. You just see the function that we have chosen, right? Power p, and we have taken that what should be the value of p, right? And then the derivative of that function. So you have to choose that like that, okay? When you are going to take the fear coefficient 0, then it should not be there. When you are going to take the I equal to 0, then there should not be that, everything will be 0. So all the properties, derivative of that you should take care. What should be that? So derivative should be less than 0 if it is going to decrease that translation rate. So mathematically you have to observe these properties of that function, and then only you have to write that. Like in 2016, there was a paper by the Wang in Journal of Mathematical Biology, when they have actually first time modeled this function here into the model. They have described everything very properly, that what are the properties, those who will follow this function, and how it is going to reduce, means the growth rate of the species. Okay, they have explained everything, and then they have chosen that function, and that should also not have any kind of similarity that you have to model like that. Otherwise it will create a problem. So in the denominator we take 1 plus alpha times e I. Why we take like this? Because when you increase the I, then this function getting lesser value, and when it is multiplied into the incidence function, then it get it down, right? Its value getting down when I is increasing. And it is saturating also, because you need the saturation level. And if there is more fear, then you are going to make it quadratic. And if you want to generalize it, then you are going to take denominator I power p, and then you adjust p according to the situation that you are modeling. Okay.
Yeah. So just to add what Dr. It is, we know the characteristics of certain functions already, which is very well known. We have tried various functions and we know how the shape look like, right? And some ideas we get it from social science papers, which tells it how the behavior will impact the output that you are looking for. So you basically fit that data which social scientists collected to get the shape, right shape, by using your properties, as Dr. Tripathi was mentioning, You already know the properties of some function. So you use those ideas and the real data from social scientists that they have already captured on a separate occasions, and that decides which functions to choose from. So it is a research in itself, what functions. One of the paper we did, it took us almost few months to decide on the nonlinearity. Systemizes paper, right? That took us
Yes, sir. That could be discussed here, but yeah, sometime we will talk about that. Yeah, it has all the things we talk about.
So thank you very much, Dr. Tripathi, actually, and let's give him a round of applause. What's next? Thank you, and I will message you later. Thank you, Dr. Tripathi.
Thank you so much, sir. Thank you so much.
Okay, so we will go on a lunch break, have a wonderful lunch, warm lunch in this cold weather, and message in the group. Are we reading the message first of all? Yes? What did he message? Special issues. So this is a good opportunity for you all to publish your work. And I would, I'm very busy also, but since I initiated it, I will keep